Hey everyone. Tonight we're diving into one of the most extraordinary transformations in the history of life on Earth. Picture this. Somewhere between 6 and 7 million years ago, in the ancient landscapes of Africa, a single lineage of apes began a journey that would eventually lead to you sitting here, watching this video, contemplating your own existence. This isn't just another evolution story. This is the story of how one particular branch on the tree of life stumbled, experimented, and ultimately rewrote the rules of what it meant to be a primate. Before we go any further, take a moment to like this video if you're genuinely curious about our origins, and let me know in the comments where you're watching from and what fascinates you most about human evolution. It's always incredible to connect with fellow seekers of knowledge from around the globe. Now, settle in, maybe grab a warm drink, and let's journey back to a time when our ancestors were still figuring out how to walk upright, one tentative step at a time. For decades, scientists painted a neat, linear picture of human evolution. Ape becomes early human becomes modern human. Simple, clean, satisfying. But here's the thing about science. It has this annoying habit of getting more complicated the deeper you dig. And in recent years, that neat little story has been completely shattered by discoveries that reveal something far more chaotic, far more experimental, and infinitely more fascinating. The reality is that human evolution wasn't a straight march from the trees to the savannah. It was more like nature throwing dozens of different versions of almost human at the wall to see what would stick. Multiple species, multiple experiments, multiple ways of being bipedal, all happening simultaneously across the African continent. Most of these experiments failed. Most of these lineages vanished without a trace. But one of them, just one, managed to survive long enough to become us. Let's start with what we know for certain. The molecular evidence, the DNA that doesn't lie, tells us that humans share their most recent common ancestor with chimpanzees, somewhere between 6 and 7 million years ago. This isn't speculation. This is hard science, confirmed by multiple independent studies using molecular clock analysis. What's particularly mind-bending about this relationship is that we're actually more closely related to chimpanzees than chimpanzees are to gorillas. Think about that for a moment. Those massive, knuckle-walking mountain gorillas that look so similar to chimps, they're actually more distant cousins to chimpanzees than we are. But here's where it gets really interesting. The story of human evolution isn't just about us. It's about understanding an entire world of ancient apes that once dominated Africa and Eurasia. Today's handful of ape species, humans, chimpanzees, gorillas, orangutans, and gibbons, represent mere scraps of what was once an incredibly diverse family. Between 23 and 5 million years ago, dozens of different ape species swung through the forests, walked across the grasslands, and experimented with every conceivable way of being an ape. Most of these species are now extinct, leaving behind only fossilized teeth, fragments of bone, and tantalizing hints of what might have been. But their legacy lives on in the genetic code and anatomical features that all modern apes, including us, still carry. The loss of tails, upright postures when needed, grasping hands, relatively large brains, flexible shoulder joints, slow maturation, and extended lifespans. These weren't human innovations. These were ape innovations that we inherited and then modified for our own peculiar purposes. The challenge for paleontologists trying to piece together our origins is that fossilization is incredibly rare, especially in the tropical forest environments where many early apes lived. Bones decay, forests don't preserve fossils well, and millions of years have a way of erasing most traces of ancient life. So when scientists do find fossils from this critical period, each discovery has the potential to rewrite textbooks. And that's exactly what's been happening over the past 2 decades. Discoveries in Chad, Kenya, Ethiopia, and other parts of Africa have been forcing scientists to completely rethink their assumptions about how, when, and where our lineage first diverged from our ape cousins. The first potential candidate for earliest human ancestor takes us to the deserts of Chad, where in 2001, researchers discovered the fossilized skull of a creature they named Sahelanthropus chadensis. This skull, affectionately nicknamed Tumai, dates back nearly 7 million years, placing it right at the edge of when genetic evidence suggests humans and chimpanzees last shared a common ancestor. Tumai's skull tells a fascinating story. It has a mixture of features that seem almost impossibly contradictory. The face projects forward like an ape's, but not as dramatically. The brow ridges are massive, like those of a gorilla, but the overall skull shape hints at something different. Most intriguingly, the foramen magnum, the large hole where the spinal cord connects to the brain, sits further forward than in any living ape. In humans, this hole is positioned directly underneath the skull because our heads sit on top of vertical spines. In quadrupedal apes, it's positioned toward the back because their heads hang forward from horizontal spines. Tumai's foramen magnum position suggests that its head was balanced on top of a more upright spine. This could mean that Sahelanthropus was already experimenting with upright posture 7 million years ago, making it a very early member of the human lineage. But here's where scientific honesty kicks in. We don't have the rest of Tumai's skeleton. We can't be certain how it moved, how it lived, or even whether it was truly bipedal. Recent analysis of an arm bone attributed to Sahelanthropus has actually raised more questions than answers. The bone's structure suggests that this creature was still spending significant time in trees and may have moved on the ground using knuckle walking, much like modern chimpanzees and gorillas. This doesn't necessarily disqualify Sahelanthropus from being an early human ancestor, but it does highlight just how experimental and transitional these early forms were. The story becomes even more intriguing when we move forward in time to about 6 million years ago and encounter Aurorin tuganensis, discovered in the Tugan Hills of Kenya. Aurorin, whose name means original man in the local language, provides some of the earliest convincing evidence for bipedal locomotion in a potential human ancestor. The thigh bones of Aurorin show clear adaptations for upright walking. The angle of the femur, the way it connects to the hip, and the distribution of bone density all point to a creature that was spending at least some of its time walking on two legs. Unlike the ambiguous evidence from Sahelanthropus, the case for bipedalism in Aurorin is much stronger. But Aurorin wasn't a modern human walking around 6 million years ago. Its teeth were still very ape-like, and it likely retained many arboreal adaptations. This creature was living in a world of lakes, streams, and woodlands, not the open savannas that later human ancestors would call home. It was experimenting with a new way of moving while still maintaining the ability to climb and forage in trees. The environment that Aurorin inhabited gives us important clues about the pressures that might have favoured bipedal locomotion. This wasn't the stereotypical African savanna with endless grasslands stretching to the horizon. This was a mosaic landscape of forests, woodlands, and open areas, constantly shifting as climate patterns changed across the continent. Perhaps the most comprehensive picture of early human evolution comes from the remarkable fossils of Ardipithecus ramidus, affectionately known as Ardi. Dating to 4.4 million years ago, Ardi represents one of the most complete early potential human ancestors ever discovered, with fossils representing multiple individuals and giving scientists unprecedented insight into how these creatures lived and moved. Ardi was a revelation because it challenged so many assumptions about what early human ancestors should look like. For decades, scientists had used chimpanzees as a model for understanding the last common ancestor of humans and apes. The logic seemed sound. Chimpanzees are our closest living relatives, so early human ancestors probably looked and behaved something like chimpanzees. Ardi demolished this assumption. This creature didn't look like a chimpanzee that was learning to walk upright. It looked like something entirely different, something that had never been seen before in the fossil record. Ardi had long, powerful arms and curved fingers perfect for climbing, but its pelvis showed clear adaptations for upright walking. Most remarkably, it had a grasping big toe, like modern apes, but the rest of its foot anatomy suggested it could walk bipedally when on the ground. What Ardi revealed was a creature perfectly adapted to live in both worlds. It could move through the trees with the skill of any ape, grasping branches, swinging from limb to limb, and foraging in the forest canopy. But when it came down to the ground, it could walk upright with the efficiency that no other ape possessed. This dual lifestyle makes perfect evolutionary sense when you consider the environment Ardi inhabited. The climate was changing, forests were fragmenting, and resources were becoming more scattered across the landscape. A creature that could exploit both arboreal and terrestrial resources would have had significant advantages over specialists that were limited to just one environment. Recent reanalysis of Ardi's anatomy has provided even more fascinating insights into early human evolution. In 2025, scientists published new research showing that Ardi's ankle anatomy actually shows similarities to modern African apes, suggesting that the common ancestor of humans and chimpanzees may have moved more like modern chimps than previously thought. This finding doesn't diminish Ardi's importance. It actually makes the story more interesting. It suggests that early human ancestors like Ardi were maintaining some ancestral ape-like locomotion while simultaneously developing new bipedal capabilities. Evolution wasn't replacing old systems with new ones. It was adding new capabilities on top of existing ones. The ankle evidence also tells us something profound about chimpanzees and gorillas. Rather than representing stepping stones on the path to human evolution, these modern apes are actually highly specialized creatures that have been evolving and adapting for just as long as we have. They're not living fossils or evolutionary leftovers. They're successful apes that found their own path to survival in African forests. This realization has forced scientists to abandon the old ladder model of evolution, where each species represented a rung on the way to modern humans. Instead, human evolution looks more like a sprawling bush with multiple branches, most of which led to extinction, and only one of which led to us. The evidence for this bushy model of human evolution becomes even stronger when we look at more recent discoveries from Ethiopia. Fossils found at sites like Ledi Diraru have revealed that multiple human-like species were living in the same regions at the same times, sometimes for hundreds of thousands of years, rather than one species evolving into the next in a neat sequence. We now know that different groups were experimenting with different solutions to the challenge of being a bipedal ape in a changing world. Some focused on developing larger brains, others on more efficient walking, still others on specialized diets or social behaviors. The remarkable diversity of these early experiments becomes even more apparent when we examine the fossil record from around 2 to 3 million years ago. During this period, Eastern Africa was home to at least 4 different lineages of human ancestors, all trying their own approaches to survival in rapidly changing environments. This wasn't a single species slowly transforming over time. This was nature running multiple parallel experiments in what it meant to be human. One of the most striking discoveries came from analyzing foot bones from different hominin species across this 2 million year window. Scientists identified 5 distinct foot structures, each representing a different way of walking upright. Think about that for a moment. 5 different solutions to the same basic problem of how to move efficiently on 2 legs while maintaining the ability to climb when necessary. These weren't minor variations on a theme. These were fundamentally different approaches to bipedalism, each with its own advantages and disadvantages. Some species developed long, curved toes that maintained excellent gripping ability for climbing, but sacrificed some efficiency in ground locomotion. Others evolved shorter, straighter toes that improved walking performance, but reduced arboreal capabilities. Still others found middle ground solutions that balanced both needs. The functional implications of these different walking styles extend far beyond simple locomotion. Imagine groups of early humans moving across the landscape, each with their own distinctive gait. From a distance, the way they walked might have served as a form of species identification. Are those figures on the horizon members of our group, or do they belong to a different lineage entirely? In a world where resources were scarce and competition was fierce, being able to quickly identify friend from potential foe could mean the difference between cooperation and conflict. This diversity in locomotion reflects the complex environmental pressures these early humans faced. The Africa of 2 to 3 million years ago was not the stable savanna often depicted in documentaries. It was a continent in constant flux, with climate patterns shifting dramatically over relatively short geological timescales. Lake levels rose and fell, forests expanded and contracted, and grasslands appeared and disappeared as rainfall patterns changed across the landscape. In this volatile environment, flexibility was key to survival. Species that locked themselves into highly specialized adaptations often found themselves trapped when conditions changed. But lineages that maintained multiple options, that could switch between different strategies as circumstances demanded, had better chances of weathering environmental upheavals. The fossil evidence reveals that many of these early human species maintained what scientists call a mosaic of features. They weren't fully committed to either arboreal or terrestrial lifestyles, but instead kept one foot in each world, literally and figuratively. Their skeletons show adaptations for climbing, swinging, and grasping alongside modifications for upright walking, running, and ground-based foraging. This transitional anatomy makes perfect sense when we consider the unpredictable nature of resources in their environment. During times when fruit was abundant in the trees, arboreal capabilities allowed access to rich, concentrated food sources. When terrestrial resources like roots, tubers, or scattered seeds became more important, bipedal locomotion provided the efficiency needed to cover large distances while foraging. Recent research has provided fascinating insights into how this flexibility might have worked in practice. Studies of modern chimpanzees show that, when valuable but unpredictable resources are discovered, individuals are more likely to switch to bipedal locomotion because it allows them to carry more food in a single trip. This behavioral flexibility suggests a possible pathway for how occasional bipedalism could have evolved into the obligate two-legged locomotion that characterizes all later human species. For early human ancestors living in an environment where the next meal was never guaranteed, the ability to monopolize and transport resources efficiently could have provided crucial survival advantages. Those individuals who could walk upright while carrying food, tools, or infants would have been able to exploit opportunities that were unavailable to their more quadrupedal relatives. The evolutionary pressure to carry resources becomes even more significant when we consider the social implications. Early human groups were likely small and highly mobile, moving across the landscape in response to seasonal changes in resource availability. The ability to transport not just food, but also tools, materials for shelter construction, and dependent offspring would have allowed these groups to range more widely and survive in more marginal environments. But bipedalism came with costs as well as benefits. Walking upright required significant anatomical reorganization, particularly in the pelvis, spine, and lower limbs. These changes had cascading effects throughout the body, influencing everything from birth mechanics to brain development. The narrowing of the pelvic opening that accompanied bipedal adaptations made childbirth more difficult and dangerous, contributing to the evolution of shorter gestation periods and the birth of increasingly helpless infants. This trade-off between locomotor efficiency and reproductive challenges helps explain why bipedalism evolved gradually, rather than appearing suddenly in the fossil record. Each step toward more committed upright locomotion required compensating changes in other body systems to maintain overall fitness and survival. The skeletal evidence from this period reveals the experimental nature of these adaptations. Different species tried different solutions to the same basic engineering problems. Some maintained relatively ape-like pelvises while developing more human-like leg bones. Others modified their spinal curvature while keeping more primitive foot structures. Each represented a different compromise between the demands of bipedal locomotion and the constraints of existing anatomy. The diversity of these experiments is perhaps best illustrated by examining the range of body sizes among early human species. Some, like certain populations of Australopithecus, were relatively small and lightly built, suggesting they maintained significant arboreal capabilities well into their evolutionary history. Others developed more robust skeletal structures that suggest greater commitment to terrestrial lifestyles and possibly more demanding foraging strategies. These size differences weren't just random variation. They likely reflected different ecological niches and survival strategies. Smaller, more gracile forms might have specialized in exploiting scattered, high-quality resources that required both climbing ability and efficient ground travel. Larger, more robust forms might have focused on processing lower quality but more abundant terrestrial foods that required powerful jaws and digestive systems. The environmental context for these experiments was shaped by long-term climate trends that were transforming the African continent. Global cooling patterns were reducing atmospheric moisture and altering precipitation patterns across much of the continent. Forests that had once covered vast areas were fragmenting into smaller patches, separated by expanding grasslands and woodland savannas. These changes created new opportunities for species that could exploit the resources of open environments while maintaining access to traditional forest foods. The edges between different habitat types became particularly important, offering diverse resources within relatively small areas, but requiring the mobility to access them efficiently. The fossil sites that preserve evidence of these early human experiments are scattered across eastern and central Africa, from Chad in the west to Ethiopia and Kenya in the east. Each location tells a slightly different story about local environmental conditions and the specific challenges faced by early human populations. Some sites preserve evidence of lakeside environments rich in aquatic resources. Others document woodland settings with diverse plant and animal communities. Still others reveal more open landscapes where long-distance travel would have been essential for survival. This geographic diversity reinforces the experimental nature of early human evolution. Different populations face different challenges and develop different solutions. Some of these local adaptations proved successful enough to spread to other regions. Others remained isolated experiments that eventually went extinct when local conditions changed. The story becomes even more complex when we consider the role of technology in this early period. While the earliest stone tools don't appear in the archaeological record until around 3.3 million years ago, it's likely that earlier human ancestors were using organic tools made from wood, bone, or other perishable materials. The use of simple tools for digging, processing food, or extracting resources from difficult-to-access locations could have provided significant advantages for bipedal species that had freed their hands from locomotor duties. The cognitive demands of tool use and manufacture may have provided additional selective pressure for the brain enlargement that would become such a prominent feature of later human evolution. But during this early experimental phase, brain size remained relatively small and ape-like across most human lineages. The major expansion of brain size wouldn't begin until after 2 million years ago, suggesting that intelligence as we understand it was not the driving force behind the initial divergence of the human lineage. Instead, the early phases of human evolution seem to have been driven primarily by locomotor and dietary adaptations. The ability to walk efficiently on two legs while maintaining climbing capabilities opened up new ecological niches that hadn't been available to earlier apes. The anatomical changes required for this dual lifestyle created the foundation upon which later innovations in brain size, tool use, and social complexity would build. As we examine the fossil evidence from this crucial period, we see a pattern of innovation, experimentation, and frequent extinction. Most of the lineages that tried different approaches to being bipedal ultimately failed to survive changing environmental conditions. But the experiments themselves were far from failures. Each represented a successful solution to the immediate challenges of survival in a particular time and place. The lineage that eventually led to modern humans wasn't necessarily superior to its extinct relatives. It was simply the one that happened to possess the right combination of adaptations when the next major environmental shift occurred. In the unpredictable world of evolution, survival often depends as much on luck and timing as on superior design. This humbling perspective reminds us that human evolution wasn't inevitable or predetermined. We exist today because one particular branch of the primate family tree managed to navigate a series of environmental and evolutionary challenges that eliminated dozens of other potential human lineages. Understanding this history helps us appreciate both the remarkable journey that led to our existence and the fragile nature of our continued survival on a planet that continues to change around us. The fossil record from this experimental period reveals something truly remarkable about the nature of evolutionary innovation. While we often think of evolution as a slow, gradual process of refinement, the early phases of human evolution show bursts of rapid experimentation followed by long periods of relative stability. This pattern, known as punctuated equilibrium, suggests that major evolutionary transitions often occur in relatively short geological timeframes when environmental pressures create new opportunities for adaptive radiation. Between 4 and 2 million years ago, Africa became a testing ground for different approaches to bipedal locomotion. The continent's climate was becoming increasingly variable, with wet and dry periods alternating on timescales of thousands to tens of thousands of years. These cyclical changes created a constantly shifting mosaic of environments that favored different survival strategies at different times. During wetter periods, forests expanded and traditional ape-like lifestyles became more viable. Species that had maintained strong climbing abilities could exploit the rich resources of expanding woodlands. But when dry periods returned, those same forests fragmented, and the ability to travel efficiently between scattered resource patches became crucial for survival. The anatomical evidence from this period shows how different lineages responded to these challenges. Some species, like certain populations of Australopithecus afarensis, developed increasingly efficient bipedal locomotion while maintaining relatively small body sizes. Their skeletons show clear adaptations for long-distance walking, with elongated leg bones and pelvic modifications that improve the mechanical efficiency of upright locomotion. Other lineages took different approaches. The robust Australopithecines developed massive jaw muscles and enlarged molars that allowed them to process tough, fibrous plant materials that became more abundant as grasslands expanded. Their skulls show distinctive sagittal crests, bony ridges along the top of the head where powerful chewing muscles attached. These creatures were essentially living nutcrackers, specialized for extracting nutrients from foods that other species couldn't effectively process. The diversity of dental adaptations among early human species reveals the range of dietary strategies they employed. Some maintained relatively small, ape-like teeth, suitable for processing fruits and other soft plant materials. Others developed enlarged grinding surfaces for processing seeds, nuts, and roots. Still others showed evidence of increasingly omnivorous diets that included significant amounts of meat. This dietary diversification had profound implications for social behavior and technological development. Species that relied heavily on scattered, hard-to-process plant foods likely spent most of their time in small foraging groups, moving constantly across the landscape in search of seasonal resources. Those that incorporated more meat into their diets may have developed more complex social structures for coordinating hunting activities and sharing kills. The earliest evidence for systematic tool use appears during this period, though the technologies involved were still quite simple. Stone tools from sites like Lomekwi in Kenya, dating to 3.3 million years ago, show that early human ancestors were deliberately shaping rocks to create sharp edges for cutting and scraping. These tools weren't sophisticated by later standards, but they represented a crucial cognitive breakthrough in the ability to modify the environment to suit specific needs. The cognitive demands of tool manufacture shouldn't be underestimated. Creating even simple stone tools requires understanding the properties of different rock types, the ability to plan a sequence of actions, and the motor skills to execute precise strikes that remove flakes in predictable patterns. These abilities suggest that early human ancestors had already developed enhanced spatial reasoning and manual dexterity compared to their ape relatives. But perhaps more importantly, tool use created new selective pressures that would shape the trajectory of human evolution for millions of years to come. Species that could effectively use tools gained access to new food sources and could process existing resources more efficiently. This technological enhancement of foraging capabilities may have allowed early human populations to survive in marginal environments that would have been uninhabitable without artificial aids. The social implications of tool use were equally significant. Unlike the relatively simple technologies used by modern apes, the stone tools created by early humans required considerable time and skill to manufacture. This investment in tool production created incentives for sharing and cooperation within groups. An individual who spent hours crafting a sharp cutting tool would benefit from sharing it with others in exchange for access to their specialized knowledge or resources. These early forms of technological cooperation laid the groundwork for the complex cultural systems that would later become such a defining feature of human societies. The ability to accumulate knowledge across generations, to build upon the innovations of predecessors, and to coordinate group activities around shared technological goals represented a fundamental departure from the more individualistic survival strategies employed by most other primates. The archaeological evidence from this period also reveals increasing sophistication in site selection and landscape use. Early human ancestors weren't simply wandering randomly across the African landscape. They were making strategic decisions about where to establish temporary camps, how to exploit seasonal resources, and when to move to new areas. Some sites show evidence of repeated occupation over thousands of years, suggesting that certain locations held particular advantages that drew human groups back repeatedly. These preferred locations often shared common characteristics that reveal important information about early human ecology. Many were situated near permanent or seasonal water sources, providing both drinking water and attracting the animals that early humans hunted or scavenged. Others were located on elevated terrain that offered good visibility across surrounding landscapes, allowing early warning of approaching dangers or opportunities. The strategic use of landscape features demonstrates that early human ancestors possessed sophisticated spatial cognition and environmental knowledge. They understood seasonal patterns of resource availability, could navigate across large territories using landmark recognition, and could plan movements that maximized foraging efficiency while minimizing risks from predators or competitors. This environmental intelligence became increasingly important as climate variability intensified during the late Pliocene and early Pleistocene periods. Between 3 and 2 million years ago, global cooling trends led to the expansion of ice sheets in northern latitudes and corresponding changes in atmospheric circulation patterns that affected precipitation across Africa. These climate shifts created new evolutionary pressures that would ultimately lead to the emergence of the first members of our own genus, Homo. The environmental challenges of this period favored species that could adapt quickly to changing conditions, exploit diverse food sources, and coordinate group activities more effectively than their competitors. The transition from Australopithecine-grade ancestors to early Homo represents one of the most significant adaptive radiations in human evolutionary history. Within a relatively short period, multiple species appeared that showed marked increases in brain size, technological sophistication, and geographic range. This evolutionary burst wasn't simply a continuation of earlier trends. It represented a qualitative shift in the trajectory of human evolution. The earliest members of genus Homo, such as Homo habilis and Homo rudolfensis, showed brain sizes nearly 50% larger than their Australopithecine contemporaries. This neurological expansion came with corresponding increases in technological capabilities. The stone tool industries associated with early Homo species were more sophisticated than earlier technologies, showing evidence of systematic approaches to tool design and manufacture. But brain enlargement came with significant costs as well as benefits. Larger brains require enormous amounts of energy to develop and maintain. The human brain, despite representing only about 2% of total body weight, consumes roughly 20% of the body's metabolic energy. For early human ancestors living in environments where food was often scarce and unpredictable, supporting larger brains would have required fundamental changes in diet and foraging strategies. The solution appears to have involved a shift toward higher quality foods that provided more calories per unit of foraging effort. This dietary transition likely included increased consumption of meat, either through hunting or scavenging, and more intensive processing of plant foods using stone tools. Both strategies would have allowed early Homo species to extract more nutrition from their environment, while spending less time and energy on food acquisition activities. The social implications of these changes were equally profound. Larger brains enabled more sophisticated forms of communication, cooperation, and social learning. Early Homo groups could coordinate activities more effectively, share information about resource locations and environmental conditions, and transmit technological knowledge from one generation to the next with greater fidelity. These enhanced social capabilities created positive feedback loops that accelerated the pace of cultural and technological evolution. As groups became more effective at exploiting their environments, they could support larger populations and more complex social structures. These larger, more complex groups could generate and maintain more sophisticated technologies, which in turn enabled them to exploit new environments and resources. The geographic expansion of early Homo species provides dramatic evidence for the success of these adaptive strategies. While Australopithecines remained largely confined to Africa, early Homo populations began dispersing into Eurasia by approximately 1.8 million years ago. This range expansion represented an unprecedented achievement for any primate species and demonstrated the effectiveness of the technological and social adaptations that characterized early human evolution. The dispersal from Africa wasn't a single migration event, but rather a series of expansions that occurred over hundreds of thousands of years. Different populations followed different routes and adapted to different environmental conditions as they encountered new challenges outside their ancestral African homeland. Some groups moved through the Levantine corridor into Western Asia, while others may have used southern Arabian routes to reach South and Southeast Asia. Each of these dispersal routes required specific adaptations to local environmental conditions. The temperate climates of Western Asia presented challenges related to seasonal resource availability and temperature fluctuations that were quite different from the tropical and subtropical environments of Africa. Early human populations had to develop new technologies for creating shelter, preserving food, and maintaining body temperature during cold periods. The archaeological evidence from early sites outside Africa shows remarkable technological innovation in response to these new challenges. Stone tool industries became more sophisticated and specialized, with different tool types designed for specific functions. Evidence for the controlled use of fire appears during this period, providing early humans with the ability to cook food, extend daylight hours, and survive in colder climates. These technological advances weren't simply copied from one group to another. They represented independent innovations that arose in response to local environmental pressures. The convergent evolution of similar technologies in different regions demonstrates the powerful selective advantages that these innovations provided for early human populations, attempting to establish themselves in new environments. The success of these early dispersals had lasting consequences for human evolutionary history. Once established outside Africa, different human populations began evolving independently in response to local environmental conditions. This geographic isolation created the conditions for the emergence of distinct regional variants that would later develop into the diverse array of human species that characterized the Middle Pleistocene period. But even as early human populations were spreading across the Old World, the African continent remained a center of evolutionary innovation. New species continued to appear in the fossil record, each representing different experiments in what it meant to be human. Some of these lineages would eventually contribute to the ancestry of modern humans, while others would become evolutionary dead ends that left no descendants. The complex pattern of species origins, extinctions, and migrations that characterize this period creates significant challenges for paleontologists attempting to reconstruct human evolutionary relationships. Unlike the relatively simple branching patterns seen in many other mammalian groups, human evolution during this period resembled a complex network of interconnected populations that periodically split apart and came back together as environmental conditions and geographic barriers changed. This reticulate pattern of evolution helps explain some of the apparent contradictions in the human fossil record. Fossils from the same time period often show mixtures of primitive and derived characteristics that don't fit neatly into linear evolutionary sequences. Rather than representing transitional forms between clearly defined species, many of these fossils may represent members of populations that were in the process of splitting apart or coming back together. Understanding this complex evolutionary history requires abandoning simple tree-like models of human evolution in favor of more sophisticated network approaches that can accommodate gene flow between diverging lineages. Modern genetic techniques are beginning to provide insights into these ancient population dynamics, revealing evidence for hybridization events and population mixing that occurred hundreds of thousands of years ago. The implications of this research extend far beyond academic paleontology. Understanding the complex, experimental nature of early human evolution provides important perspectives on human diversity and the arbitrary nature of racial classifications. The genetic evidence makes clear that modern human populations represent a continuous spectrum of variation rather than discrete categories, and that this variation reflects the complex history of population movements and mixing that has characterized human evolution from its earlier stages. Perhaps most importantly, studying early human evolution reminds us of the contingent nature of our own existence. The lineage that led to modern humans wasn't inevitable or predetermined. It was one of many possible outcomes of the evolutionary process. Dozens of other human species lived and thrived for millions of years before eventually succumbing to environmental changes, competition, or simple bad luck. This perspective should instill both humility and wonder as we contemplate our place in the natural world. We are not the pinnacle of evolution or the inevitable result of natural selection. We are the temporary winners in an ongoing experiment that has been running for millions of years and will continue long after our own species has vanished from the Earth. The story of early human evolution also highlights the importance of environmental change as a driver of evolutionary innovation. The climatic instability that characterized the late Pliocene and early Pleistocene periods created the selective pressures that drove the evolution of intelligence, technology, and social cooperation in our lineage. Without these environmental challenges, it's entirely possible that human ancestors would have remained relatively simple apes living in African forests. But environmental change is a double-edged sword that can just as easily drive species to extinction as promote evolutionary innovation. The same climatic instability that spurred human evolution also eliminated dozens of other primate species that were unable to adapt quickly enough to changing conditions. The lesson for modern humans facing rapid anthropogenic environmental change should be clear. Our technological capabilities and social complexity provide some buffer against environmental disruption, but they don't make us immune to the forces that have shaped evolutionary history for billions of years. As we continue to uncover new fossils and develop more sophisticated analytical techniques, our understanding of early human evolution will undoubtedly continue to evolve. Each new discovery has the potential to overturn established theories and reveal new complexities in the story of how one particular lineage of African apes eventually gave rise to the remarkable diversity of modern human cultures and societies. The revolutionary discoveries that would truly transform our understanding of human origins were still to come. By the time we reach the period between 2.8 and 2.5 million years ago, the African landscape had become a laboratory for what scientists now recognize as one of the most dramatic adaptive radiations in primate history. Multiple human lineages were not just coexisting, they were actively competing for resources, territory, and ultimately, survival itself. The fossil sites of Eastern Africa from this period tell a story that would have seemed impossible just decades ago. At Ledijararu in Ethiopia, paleontologists uncovered evidence that fundamentally challenged everything scientists thought they knew about human evolution. The teeth and jaw fragments discovered there revealed the existence of a previously unknown species of Australopithecus that lived alongside some of the earliest members of our own genus, Homo. Think about the implications of this discovery for a moment. For over a century, scientists had constructed neat family trees showing one species evolving into the next in orderly succession. Australopithecus led to early Homo, which led to more advanced Homo, which eventually led to us. Clean, simple, satisfying. But the Ledijararu discoveries shattered this comfortable narrative entirely. What the fossils revealed was a much messier, much more chaotic picture. Between 2.6 and 2.8 million years ago, Eastern Africa was home to at least 4 distinct human lineages, each pursuing its own evolutionary strategy, each adapted to slightly different ecological niches, each representing a different experiment in what it meant to be human. Some focused on developing more sophisticated tools and larger brains. Others specialized in processing tough plant materials with massive grinding teeth. Still others maintained more generalized adaptations that allowed them to exploit whatever resources were available. This wasn't a ladder with humans climbing steadily upward towards some predetermined goal. This was a bush, spreading in multiple directions simultaneously, with most branches eventually withering and dying, while only one managed to survive long enough to produce descendants that would eventually become us. The environmental context for this explosive diversification becomes clearer when we examine the geological and climatic evidence from this crucial period. Africa was undergoing dramatic transformations driven by global cooling trends that were fundamentally altering atmospheric circulation patterns. The expansion of ice sheets in the northern hemisphere was creating new weather systems that brought increased seasonality and unpredictability to much of the African continent. Lake levels fluctuated wildly as rainfall patterns shifted across timescales of thousands to tens of thousands of years. Forests that had remained stable for millions of years began fragmenting into isolated patches separated by expanding grasslands. Rivers changed course, creating new barriers to movement while opening up previously inaccessible valleys and highlands. For the early human species trying to make a living in this volatile landscape, adaptability became the key to survival. Those lineages that had locked themselves into highly specialized ecological niches often found themselves trapped when environmental conditions shifted. A species perfectly adapted to life in dense woodlands might thrive during wet periods when forests expanded, but face extinction when dry cycles returned and their preferred habitats disappeared. The successful lineages were those that maintained what evolutionary biologists call adaptive flexibility. They could switch between different foraging strategies as circumstances demanded, exploit multiple types of resources, and adjust their behavior patterns in response to changing environmental conditions. This flexibility required not just anatomical adaptations, but increasingly sophisticated cognitive abilities. The neurological demands of surviving in unpredictable environments may help explain one of the most striking features of human evolution during this period, the rapid expansion of brain size. Between 3 and 2 million years ago, some human lineages began developing significantly larger brains than their predecessors. This neurological enhancement didn't happen gradually over millions of years. It occurred relatively rapidly in evolutionary terms, suggesting intense selective pressure for enhanced cognitive capabilities. But brain enlargement came with enormous costs that would have been prohibitive unless the benefits were equally substantial. Large brains require vast amounts of energy to develop and maintain. They also necessitate longer developmental periods, during which young individuals remain dependent on adult care. For species living in harsh, unpredictable environments where food was often scarce, supporting larger brains would have required fundamental changes in diet, social organization, and child-rearing practices. The solution appears to have involved a coordinated suite of adaptations that allowed early human groups to extract more calories from their environment while reducing the costs of brain development through enhanced social cooperation. Archaeological evidence from this period shows increasing sophistication in stone tool technologies, suggesting that early humans were becoming more effective at processing both plant and animal foods. The stone tools themselves tell a fascinating story of technological evolution. The earliest implements were relatively simple, consisting of rocks that had been deliberately shaped to create sharp cutting edges. But by 2.5 million years ago, toolmakers were creating more specialized instruments designed for specific functions. Some tools were optimized for cutting meat and breaking bones to access nutritious marrow. Others were shaped for digging roots and tubers from hard ground. Still others were designed for processing tough plant fibers or wooden materials. This technological diversification reflects increasingly sophisticated understanding of material properties and manufacturing techniques. Creating effective stone tools requires knowledge of how different rock types fracture, the ability to plan complex sequences of actions, and the motor skills to execute precise strikes that remove flakes in predictable patterns. These cognitive demands suggest that early toolmakers possessed enhanced spatial reasoning, manual dexterity, and working memory compared to their non-tool using relatives. Perhaps more importantly, the standardization visible in tool assemblages from this period indicates that manufacturing techniques were being transmitted between individuals and across generations. This cultural transmission of technological knowledge represents a fundamental departure from the trial and error learning that characterizes most animal behavior. Early humans were beginning to accumulate knowledge over time, building upon the innovations of their predecessors rather than starting from scratch with each generation. The social implications of this technological revolution were equally profound. Tool manufacture and use created new opportunities for cooperation and resource sharing within groups. An individual who invested time and energy in creating specialized implements would benefit from sharing them with others in exchange for access to their knowledge, skills, or resources. These reciprocal relationships laid the groundwork for the complex social networks that would become such a defining feature of later human societies. Evidence for increasingly sophisticated social behavior during this period comes not just from tool technologies, but from the fossil sites themselves. Many locations show evidence of repeated occupation over thousands of years, suggesting that early human groups were returning to favored locations on a regular basis. These sites weren't random camping spots chosen for convenience. They were strategically selected locations that offered specific advantages for survival. The most successful sites typically combined several desirable characteristics. They were located near reliable water sources that provided drinking water and attracted the animals that early humans hunted or scavenged. They offered good visibility across surrounding landscapes, allowing early warning of approaching opportunities or threats. They provided access to high-quality raw materials for tool manufacture, including specific types of stone that were particularly well suited for creating sharp, durable implements. Some sites show evidence of more complex behaviors that suggest early humans were beginning to modify their environment in systematic ways. Stone circles at certain locations may represent the foundations of temporary shelters or windbreaks. Concentrations of broken bones and stone tools indicate areas where specific activities like butchering or tool manufacture took place repeatedly. These behavioral signatures suggest that early human groups possessed sophisticated spatial cognition and could organize their activities around planned use of landscape features. The strategic use of landscape resources becomes even more impressive when we consider the scale of the territories that early human groups apparently exploited. Analysis of stone tool raw materials shows that some implements were manufactured from rocks that originated dozens of kilometers from where they were eventually discarded. This indicates that early humans were either traveling vast distances during their foraging expeditions or participating in exchange networks that allowed valuable materials to move between different groups. Either scenario suggests remarkable cognitive sophistication. Long-distance foraging requires detailed spatial memory, the ability to navigate across complex terrain using landmark recognition, and sophisticated planning to coordinate movements with seasonal resource availability. Exchange networks require even more complex social and cognitive abilities, including the capacity to maintain relationships with distant groups, understand concepts of value and reciprocity, and coordinate timing of encounters across large geographic areas. The evidence for long-distance movements and possible exchange relationships hints at another crucial development during this period: the emergence of more complex communication systems. Coordinating group movements across large territories, maintaining social relationships with distant allies, and transmitting technological knowledge between generations would all have been facilitated by enhanced communication abilities. While direct evidence for early human communication systems is obviously lacking from the fossil record, indirect evidence suggests that significant advances were occurring. The standardization of tool technologies across wide geographic areas implies that manufacturing techniques were being transmitted with sufficient precision to maintain consistent standards. This level of cultural transmission typically requires more sophisticated communication than the simple gestural or vocal signals used by most other primates. The cognitive demands of tool manufacture itself may have provided selective pressure for enhanced communication abilities. Teaching someone to create effective stone tools requires the ability to break down complex motor sequences into discrete steps, demonstrate proper techniques, and provide feedback about performance. These instructional activities are much more efficient when supported by symbolic communication systems that can convey abstract concepts about goals, methods, and standards. Recent research on modern hunter-gatherer societies provides insights into how these early communication systems might have functioned. Contemporary groups that rely heavily on stone tool technologies typically possess elaborate vocabularies for describing different rock types, fracture patterns, and manufacturing techniques. They use specialized gestural systems to supplement verbal instructions during tool-making activities. They maintain detailed oral traditions that preserve knowledge about resource locations, seasonal patterns, and historical events across multiple generations. While we can't know exactly how early human communication systems functioned, the archaeological evidence suggests they were becoming increasingly sophisticated during this crucial period between 3 and 2 million years ago. The ability to share complex information efficiently would have provided enormous advantages for groups trying to survive in unpredictable environments where knowledge about resource locations, environmental conditions, and technological innovations could mean the difference between life and death. The enhanced communication abilities that developed during this period may also help explain another striking feature of human evolution: the rapid geographic expansion that began around 1.8 million years ago. The first human populations to leave Africa and establish themselves in Eurasia possessed technological and social capabilities that were unprecedented among primate species. They could create sophisticated tools, coordinate group activities across large territories, and maintain cultural knowledge across generations. These abilities allowed early human migrants to adapt to environmental conditions that were completely unlike anything their African ancestors had experienced. The temperate climates of Western Asia presented challenges related to seasonal temperature fluctuations, different patterns of resource availability, and unfamiliar plant and animal communities. Successful adaptation to these new environments required rapid innovation in technologies for creating shelter, preserving food, and maintaining body temperature during cold periods. The archaeological record from early sites outside Africa shows remarkable technological creativity in response to these new challenges. Stone tool industries became more sophisticated and specialized, with different tool types designed for specific functions related to local environmental conditions. Evidence for the controlled use of fire appears during this period, providing early humans with the ability to cook food, extend useful daylight hours, and survive in climates that would have been uninhabitable without artificial heat sources. The mastery of fire represents one of the most significant technological breakthroughs in human history, comparable in importance to the development of agriculture or the Industrial Revolution. Fire provided access to new food sources through cooking, which made many plant materials more digestible and reduced the time and energy required for food processing. It extended the useful day by providing light for activities after dark. It offered protection from predators and dangerous weather conditions. Perhaps most importantly, it created new opportunities for social interaction and cultural transmission during the evening hours when groups gathered around hearths. The social implications of fire use were particularly significant for early human groups attempting to establish themselves in new environments. Hearths became focal points for group activities, creating opportunities for sharing information about local conditions, coordinating future activities, and maintaining social bonds during stressful periods. The knowledge required to create and maintain fires also became another form of cultural information that needed to be transmitted between generations, further enhancing the importance of effective communication systems. But the success of early human migrants in adapting to new environments came with costs as well as benefits. Once established outside Africa, different populations began evolving independently in response to local environmental conditions. Geographic isolation reduced gene flow between distant populations and created opportunities for genetic drift and local adaptation to accumulate over time. This geographic separation had lasting consequences for human evolutionary history. By 1 million years ago, human populations in different regions of the Old World were beginning to show distinct anatomical characteristics that reflected both genetic drift and adaptation to local environmental conditions. Populations in colder climates developed anatomical features that enhanced heat retention. Those in more arid environments showed adaptations for water conservation. Groups that relied heavily on different food sources developed corresponding changes in dental and digestive anatomy. The diversification of human populations across the Old World created a complex pattern of regional variance that would characterize human evolution for the next million years. Some of these regional lineages would eventually contribute to the ancestry of modern humans through episodes of interbreeding and gene flow. Others would become evolutionary dead ends that left no genetic legacy in contemporary populations. Meanwhile, back in Africa, human evolution continued to generate new experiments in what it meant to be human. The continent that had given birth to the human lineage remained a center of evolutionary innovation throughout this period, producing new species that pushed the boundaries of brain size, technological sophistication, and social complexity even further. The African fossil record from between 2 and 1 million years ago reveals an astonishing diversity of human forms. Some species developed massive skulls with enlarged brain cases that approach the size of modern human brains. Others maintained more modest neurological endowments, while specializing in different aspects of technology or social behavior. Still others experimented with body size and proportions that were unlike anything seen in earlier human ancestors. This continued diversification within Africa, while human populations were simultaneously spreading across Eurasia, created a complex geographic pattern of human evolution. Rather than a simple out-of-Africa migration followed by regional isolation, the evidence suggests ongoing connections between African and Eurasian populations through episodic migrations and gene flow events. Genetic studies of ancient DNA are beginning to reveal the complexity of these ancient population dynamics. Evidence for interbreeding between different human lineages appears repeatedly throughout the archaeological and genetic records, suggesting that the boundaries between different human species were often more porous than traditional taxonomic classifications would suggest. This genetic evidence has profound implications for how we understand human diversity and classification. Rather than representing discrete categories with clear boundaries, different human populations appear to have formed a continuous network of interconnected groups that periodically split apart and came back together as environmental conditions and geographic barriers changed over time. The reticulate nature of human evolution helps explain many of the apparent contradictions in the fossil record. Specimens from the same time period often show combinations of characteristics that don't fit neatly into linear evolutionary sequences. Rather than representing transitional forms between clearly defined species, many of these fossils may reflect members of populations that were in the process of diverging or converging through gene flow and hybridization. Understanding this complex evolutionary history requires sophisticated analytical approaches that can accommodate the messy realities of ancient population dynamics. Simple tree-like models that assume clean splits between lineages are inadequate for capturing the true complexity of human evolutionary relationships. Instead, scientists are developing network-based approaches that can model gene flow, population mixing, and reticulate evolution more accurately. The implications of this research extend far beyond academic paleontology into contemporary discussions about human diversity and classification. The genetic evidence makes clear that modern human populations represent points along a continuous spectrum of variation rather than discrete categories with meaningful biological boundaries. The genetic differences that exist between contemporary populations pale in comparison to the diversity that characterized human evolution over the past 2 million years. This perspective should fundamentally alter how we think about concepts like race and ethnicity. Rather than reflecting deep biological divisions, these categories represent relatively recent cultural constructions that bear little relationship to the underlying patterns of genetic variation that actually characterize our species. The complex history of population movements, mixing, and local adaptation that shaped human evolution makes it clear that any attempt to divide humans into discrete biological categories is both scientifically unjustified and historically naive. Perhaps most importantly, studying the experimental nature of early human evolution provides crucial insights into the contingent nature of our own existence. The lineage that eventually led to modern humans wasn't the inevitable outcome of natural selection or the predetermined goal of evolutionary progress. It was one of many possible results of a complex process that involved chance events, environmental fluctuations, and historical accidents that could easily have unfolded differently. Dozens of other human lineages lived successful lives for hundreds of thousands or even millions of years before eventually succumbing to environmental changes, competition from other species, or simple demographic bad luck. Some of these extinct lineages possessed remarkable adaptations that in many ways surpassed those of our own ancestors. They developed sophisticated technologies, complex social systems, and impressive cognitive abilities that allowed them to thrive in challenging environments for vast periods of time. The fact that these lineages ultimately went extinct while ours survived doesn't reflect any inherent superiority on our part. It simply demonstrates that evolution is not a progressive march toward predetermined goals, but rather an ongoing experiment in which survival depends as much on luck and timing as on adaptive fitness. The environmental challenges that drove our ancestors to develop larger brains, more sophisticated tools, and enhanced social cooperation could just as easily have led to their extinction if conditions had been slightly different. This humbling perspective should instill both wonder and responsibility as we contemplate our place in the natural world. We are not the pinnacle of evolution or the intended outcome of natural selection. We are temporary participants in an ongoing process that has been unfolding for billions of years and will continue long after our own species has vanished from Earth. The story of early human evolution also highlights the crucial role of environmental change as both a creative and destructive force in evolutionary history. The climatic instability that characterized the late Pliocene and early Pleistocene periods created the selective pressures that drove the evolution of intelligence, technology, and social cooperation in our lineage. Without these environmental challenges, human ancestors might well have remained relatively simple apes, living quiet lives in African forests. But environmental change remains a double-edged sword that can drive species to extinction just as readily as it promotes evolutionary innovation. The same climatic fluctuations that spurred human brain evolution also eliminated countless other species that were unable to adapt quickly enough to changing conditions. The fossil record of this period is littered with the remains of once successful lineages that fell victim to environmental shifts they couldn't survive. For modern humans facing rapid anthropogenic environmental change, the lessons from our evolutionary past are both encouraging and sobering. Our technological capabilities and social complexity do provide some buffer against environmental disruption, allowing us to modify our surroundings and coordinate responses to challenges in ways that were unavailable to our ancestors. But these advantages don't make us immune to the fundamental forces that have shaped evolutionary history for billions of years. The pace of contemporary environmental change is unprecedented in human evolutionary history, occurring over decades rather than the thousands or millions of years that characterized past climatic shifts. While our technological abilities give us theoretical capabilities for responding to these challenges, our actual track record of coordinating effective responses to global environmental problems remains disappointingly limited. Understanding the experimental nature of evolution also provides important perspective on the future of our own species. Just as early human lineages diversified into multiple forms that explored different adaptive strategies, modern human populations may be beginning to diverge in response to different environmental and social pressures. Technological advances in genetic engineering, artificial intelligence, and space exploration are creating new possibilities for human adaptation that were unimaginable even a few decades ago. Whether these emerging capabilities will enhance human survival prospects or create new vulnerabilities remains to be seen. The history of evolution suggests that innovations which seem advantageous in the short term can become liabilities when conditions change. The massive brains that gave our ancestors competitive advantages during the Pleistocene may prove to be metabolic burdens in a world with different challenges. The technological systems that currently support human civilization could become points of failure if they prove unable to adapt to changing circumstances. The experimental nature of evolution means that there are no guarantees about future success, regardless of how well adapted a species appears to be at any given moment. The most we can do is try to maintain the adaptive flexibility that allowed our ancestors to survive previous environmental challenges while remaining humble about our ability to predict or control the forces that will shape our future evolutionary trajectory. As paleontologists continue to uncover new fossils and develop more sophisticated analytical techniques, our understanding of early human evolution will undoubtedly continue to evolve. Each new discovery has the potential to overturn established theories and reveal new complexities in the story of how one particular lineage of African apes eventually gave rise to the remarkable diversity of human cultures and societies that characterize our contemporary world. The emerging picture suggests that human evolution was far more complex, experimental, and contingent than previous generations of scientists imagined. Rather than a simple progression from primitive to advanced forms, our evolutionary history resembles a vast branching network of interconnected experiments, most of which ended in extinction, while a fortunate few managed to survive long enough to contribute to the ancestry of modern humans. This perspective transforms how we understand both our relationship to other species and our responsibility for the future of life on Earth. We are not separate from or superior to the natural world, but rather integral participants in an ongoing evolutionary process that connects us to every other form of life through billions of years of shared history. The same creative forces that shaped our ancestors continue to operate today, generating new possibilities and eliminating old forms in an endless cycle of experimentation and selection. Understanding this connection should inspire both humility about our place in the natural world and determination to use our remarkable capabilities responsibly. We are the inheritors of an extraordinary evolutionary legacy that spans millions of years and countless generations of ancestors who survived against impossible odds. We are also the first species in Earth's history to possess the ability to consciously influence the future direction of evolution, both for ourselves and for the countless other species with whom we share this planet. The choices we make today about how to use our technological capabilities, how to organize our societies, and how to relate to the natural world will determine not just our own future, but the future of the evolutionary process itself. The experimental nature of evolution means that there are no predetermined outcomes, only the endless generation of new possibilities from which natural selection and human choice will determine which forms survive and which disappear into the fossil record of the future. The weight of this realization becomes even more profound when we examine what happened to the lineages that didn't make it. The fossil record from this period is filled with remarkable species that possess their own unique solutions to the challenges of survival, yet ultimately vanished without leaving descendants in the modern world. Take the robust Australopithecines, for instance. These were extraordinary creatures that had solved the problem of survival in increasingly arid environments by developing some of the most powerful chewing apparatus ever seen in a primate. Their skulls featured massive sagittal crests, bony ridges that ran along the top of the head like a mohawk, providing attachment points for jaw muscles so large they could generate crushing forces that would make a modern gorilla envious. These creatures had essentially turned themselves into living nutcrackers, capable of processing the toughest seeds, roots, and fibrous plant materials that became increasingly abundant as Africa's climate dried out. Their molar teeth were enormous grinding platforms that could reduce almost any plant material to digestible pulp. They had found their niche and exploited it with remarkable efficiency. For over 1 million years, these robust species thrived across eastern and southern Africa. They were successful by any reasonable measure, maintaining stable populations and adapting to environmental changes that eliminated many other lineages. Their specialized adaptations allowed them to exploit food sources that were essentially unavailable to other species, giving them what seemed like an unassailable competitive advantage. But specialization, as evolution repeatedly demonstrates, is a double-edged sword. When environmental conditions shifted again around 1 million years ago, the very adaptations that had made robust Australopithecines so successful became liabilities. Their massive chewing apparatus required enormous amounts of energy to maintain. Their specialized digestive systems were optimized for processing low-quality plant materials, but couldn't efficiently extract nutrients from the higher-quality foods that became more important as environments changed. Meanwhile, other human lineages that had maintained more generalized adaptations found themselves better positioned to exploit new opportunities. The early members of genus Homo, with their smaller teeth but larger brains, could use tools to process foods that robust Australopithecines had to chew with brute force. They could hunt animals, cook plant materials to make them more digestible, and extract resources from environments that were inaccessible to more specialized species. The extinction of the robust Australopithecines represents one of the most poignant chapters in human evolutionary history. These weren't primitive failures that deserved to disappear. They were highly sophisticated creatures that had solved complex survival challenges through millions of years of evolutionary refinement. Their disappearance reminds us that even the most successful adaptations can become evolutionary dead ends when circumstances change. This pattern of specialization followed by extinction repeated itself throughout human evolutionary history. The archaeological record reveals numerous lineages that developed remarkable adaptations for specific environments or lifestyles, only to vanish when conditions shifted beyond their adaptive limits. Some species became expert climbers but lost the ability to travel efficiently on the ground. Others developed sophisticated hunting techniques but couldn't survive when prey species migrated or went extinct. The lineages that ultimately survived were those that maintained what biologists call adaptive flexibility. Rather than committing fully to any single survival strategy, they kept multiple options open. They could climb when necessary, but also walk efficiently on the ground. They could process plant foods, but also exploit animal resources when available. They could use simple tools, but also survive without them when materials weren't available. This flexibility came with costs of its own. Generalized adaptations are typically less efficient than specialized ones for any particular task. A creature that can both climb and walk will probably do neither as well as species that specialize in one or the other. A brain that can handle multiple cognitive demands will probably be less efficient at any single task than one optimized for specific functions. But in unpredictable environments where survival challenges could change rapidly and dramatically, these inefficiencies were more than compensated by the advantages of maintaining multiple options. Species that could switch between different strategies as circumstances demanded had better chances of surviving environmental upheavals that eliminated their more specialized competitors. The cognitive demands of maintaining this adaptive flexibility may help explain one of the most distinctive features of human evolution: the dramatic expansion of brain size that occurred between 2 and 1 million years ago. Managing multiple survival strategies simultaneously requires sophisticated decision-making abilities that go far beyond the relatively simple behavioral repertoires of most other primates. Early humans had to constantly evaluate environmental conditions, assess available resources, choose appropriate technologies, coordinate group activities, and plan future actions based on incomplete information about changing circumstances. These cognitive demands created intense selective pressure for enhanced memory, reasoning ability, and social intelligence that ultimately led to the development of the remarkably large and complex brains that characterize our lineage. But brain evolution wasn't simply a matter of getting bigger. The internal organization of human brains also underwent dramatic changes during this period. Regions associated with tool use, language processing, and social cognition expanded disproportionately compared to areas that handle basic sensory and motor functions. The human brain became not just larger than those of other primates, but fundamentally reorganized to support the complex behavioral repertoires that characterized our ancestors. This neurological reorganization had cascading effects throughout human development and behavior. Larger brains required extended developmental periods during which young individuals remained dependent on adult care while their nervous systems matured. This extended childhood created new opportunities for learning and cultural transmission, but also increased the costs of reproduction for early human groups. The solution appears to have involved fundamental changes in social organization that distributed childcare responsibilities among multiple group members, rather than relying solely on biological parents. Archaeological evidence from this period suggests that early human groups were developing more complex cooperative networks that allowed them to support larger numbers of dependent offspring while maintaining the mobility necessary for survival in challenging environments. These enhanced social systems created positive feedback loops that accelerated the pace of cultural and technological evolution. Larger groups could generate and maintain more sophisticated technologies. More complex social networks could coordinate activities across larger territories and longer timescales. Enhanced communication systems could transmit more detailed information about resources, environmental conditions, and technological innovations. The archaeological record from sites dating to around 1 million years ago shows dramatic increases in the sophistication and standardization of stone tool technologies. Toolmakers were creating implements that required complex sequences of actions to manufacture and showed evidence of careful planning and design. Some tools were clearly designed for specific functions, while others represented multi-purpose implements that could be adapted to various tasks as circumstances demanded. This technological sophistication extended beyond simple tool manufacture to include more complex behaviors, like the systematic use of fire, the construction of temporary shelters, and the development of food processing techniques that made previously inedible resources nutritionally available. Early human groups were beginning to modify their environments in systematic ways that enhanced their survival prospects while reducing their dependence on natural resource distributions. The mastery of these technologies wasn't simply a matter of individual innovation. The standardization visible in tool assemblages from widely separated geographic locations indicates that manufacturing techniques were being transmitted between groups and across generations with remarkable fidelity. This cultural transmission of technological knowledge represented a qualitative shift in the way information was preserved and accumulated over time. Unlike the trial and error learning that characterizes most animal behavior, early humans were developing systems for preserving successful innovations and building upon the discoveries of previous generations. This cumulative cultural evolution allowed technological sophistication to increase over time in ways that would have been impossible if each generation had to rediscover everything from scratch. The social implications of cumulative cultural evolution were equally profound. Groups that could effectively preserve and transmit technological knowledge gained enormous advantages over those that relied solely on individual learning. This created new selective pressures for enhanced communication abilities, social cooperation, and the cognitive skills necessary for effective teaching and learning. Evidence for increasingly sophisticated communication systems during this period comes from multiple sources. The standardization of tool technologies across large geographic areas suggests that manufacturing techniques were being transmitted with sufficient precision to maintain consistent standards. The coordination of group activities implied by archaeological site distributions indicates that early humans could share complex information about resource locations, environmental conditions, and planned movements. Perhaps most importantly, the preservation of technological innovations across generations required the ability to break down complex behaviors into teachable components and transmit abstract concepts about goals, methods, and standards. These instructional activities would have been much more efficient with symbolic communication systems that could convey information about things that weren't immediately present in the environment. While direct evidence for early human communication systems is obviously lacking from the fossil record, indirect evidence suggests that significant advances were occurring. The cognitive demands of the increasingly complex technologies and social behaviors visible in the archaeological record would have been difficult to support without corresponding advances in communication abilities. Recent studies of modern hunter-gatherer societies provide insights into how these early communication systems might have functioned. Contemporary groups that rely heavily on traditional technologies typically possess elaborate vocabularies for describing materials, techniques, and environmental conditions. They use sophisticated gestural systems to supplement verbal communication during instructional activities. They maintain detailed oral traditions that preserve crucial knowledge across multiple generations. The development of enhanced communication abilities during this period may also help explain another remarkable feature of human evolution: the rapid geographic expansion that began around 1.8 million years ago. The first human populations to successfully establish themselves outside Africa, possessed unprecedented abilities to coordinate group activities, share information about local conditions, and maintain cultural knowledge across generations. These capabilities allowed early human migrants to adapt to environmental conditions that were completely unlike anything their African ancestors had experienced. The temperate and subtropical climates of Western and Southern Asia presented entirely new challenges related to seasonal resource availability, temperature fluctuations, and unfamiliar plant and animal communities. Successful adaptation to these novel environments required rapid innovation in multiple domains simultaneously. Early migrants had to develop new technologies for creating shelter and maintaining body temperature during cold periods. They had to identify edible plants and animals in ecosystems they had never encountered. They had to modify their hunting and foraging strategies to exploit resources that were distributed differently across space and time than those in their ancestral African habitats. The archaeological evidence from early sites outside Africa shows remarkable technological creativity in response to these challenges. Stone tool industries became more sophisticated and regionally specialized, with different tool types designed for specific functions related to local environmental conditions. Evidence for controlled use of fire appears consistently at sites from this period, providing early humans with abilities to cook food, extend useful daylight hours, and survive in climates that would have been uninhabitable without artificial heat sources. The controlled use of fire represents one of the most significant technological breakthroughs in human evolutionary history. Fire provided access to entirely new categories of food through cooking, which made many plant materials more digestible and reduced the time and energy required for food processing. It extended the useful day by providing light for activities after dark. It offered protection from predators and dangerous weather conditions. Perhaps most importantly from a social perspective, fire created new focal points for group interaction during evening hours when other activities were limited by darkness. Hearths became centers for information sharing, social bonding, and cultural transmission that enhanced group cohesion while providing opportunities for planning future activities and coordinating responses to local challenges. The knowledge required to create and maintain fires also represented another form of cultural information that needed to be transmitted between generations. Firemaking requires understanding of appropriate materials, proper techniques for generating initial sparks, and methods for maintaining controlled combustion over extended periods. This knowledge was too complex and too crucial for survival to be left to individual discovery, creating additional selective pressure for effective teaching and learning systems. The mastery of fire technology had cascading effects on other aspects of early human behavior and ecology. Cooking allowed access to new food sources and improved the nutritional value of existing ones, potentially supporting the continued brain expansion that characterized this period. Extended daylight hours created new opportunities for tool manufacture, social interaction, and other activities that enhanced group survival prospects. Fire also provided early humans with their first systematic method for modifying local environments to suit their needs. Controlled burning could be used to clear vegetation, drive game animals, and promote the growth of useful plant species. These landscape modification techniques allowed early human groups to enhance the productivity of their territories while reducing their dependence on natural resource distributions. But the benefits of fire technology came with new risks and challenges as well. Maintaining fires required constant attention and access to appropriate fuel sources. Uncontrolled fires could destroy equipment, attract unwanted attention from predators or competitors, and pose direct threats to group safety. The social coordination required for effective fire management created new demands for cooperation and communication within early human groups. The successful integration of fire technology into early human lifestyles required sophisticated understanding of risk management, resource planning, and social coordination that went far beyond the capabilities of any other primate species. This technological mastery demonstrates the remarkable cognitive and social sophistication that early human groups had achieved by 1 million years ago. The geographic expansion enabled by these technological and social innovations had profound consequences for subsequent human evolution. Once established outside Africa, different populations began evolving independently in response to local environmental conditions and selective pressures. Geographic separation reduced gene flow between distant groups and created opportunities for genetic drift and local adaptation to accumulate over extended periods. By 500,000 years ago, human populations in different regions of the Old World were beginning to show distinct anatomical characteristics that reflected both random genetic changes and adaptive responses to local environments. Populations in colder northern climates developed features that enhanced heat retention and metabolic efficiency. Groups in more arid environments showed adaptations for water conservation and heat dissipation. Populations that relied on different food sources developed corresponding changes in dental and digestive anatomy. This geographic diversification created a complex pattern of regional variance that would characterize human evolution for hundreds of thousands of years. Some regional lineages would eventually contribute genetic material to the ancestry of modern humans through episodes of interbreeding and gene flow. Others would become evolutionary dead ends that left no descendants in contemporary populations. Meanwhile, Africa continued to serve as a center of human evolutionary innovation throughout this period. The continent that had given birth to the human lineage remained home to diverse populations that were experimenting with new approaches to brain organization, technological sophistication, and social complexity. Many of the most significant advances in human evolution continue to originate in African populations before spreading to other regions through migration and cultural transmission. The African fossil record from between 1 million and 200,000 years ago reveals continued experimentation with different approaches to being human. Some lineages developed increasingly large brains that approached or even exceeded the size of modern human brains. Others maintained more modest neurological endowments while specializing in particular technological or social innovations. Still others experimented with body proportions and anatomical features that were unlike anything seen in earlier human ancestors. This continued diversification within Africa, while human populations were simultaneously spreading and differentiating across Eurasia, created an increasingly complex global pattern of human evolution. Rather than simple out-of-Africa migrations, followed by regional isolation, the evidence suggests ongoing connections between African and Eurasian populations through episodic migrations, trade networks, and gene flow events that maintain genetic and cultural connections across vast geographic distances. Recent advances in ancient DNA analysis are beginning to reveal the complexity of these prehistoric population dynamics. Genetic evidence for interbreeding between different human lineages appears repeatedly throughout the archaeological record, suggesting that the boundaries between different human populations were often more porous than traditional species classifications would suggest. This genetic evidence has revolutionary implications for understanding human diversity and evolution. Rather than representing discrete categories with clear boundaries, different human populations appear to have formed complex networks of interconnected groups that periodically split apart and came back together as environmental conditions, technological capabilities, and social organizations changed over time. The reticulate nature of human evolution helps explain many apparent contradictions in the fossil record. Specimens from the same geographic regions and time periods often display combinations of anatomical characteristics that don't fit neatly into linear evolutionary sequences. Rather than representing transitional forms between clearly defined species, many of these fossils may reflect members of populations that were actively exchanging genetic material through interbreeding and migration. Understanding this complex evolutionary history requires analytical approaches that can accommodate the messy realities of ancient population dynamics. Simple, tree-like models that assume clean splits between lineages are inadequate for capturing the true complexity of human evolutionary relationships. Instead, scientists are developing network-based approaches that can model gene flow, population mixing, and reticulate evolution more accurately. These methodological advances are revealing that human evolution was even more experimental and contingent than previous research had suggested. The lineages that survived to contribute to modern human ancestry weren't necessarily superior to their extinct relatives in any objective sense. They were simply the ones that happened to possess the right combinations of characteristics when particular environmental challenges arose or opportunities became available. This perspective has profound implications for how we understand our own place in the natural world and our relationships with other species. We are not the inevitable products of evolutionary progress or the predetermined goals of natural selection. We are temporary participants in an ongoing experiment that has been running for millions of years and will continue long after our own species has disappeared. The humbling recognition of our contingent existence should inspire both wonder at the remarkable chain of events that led to our emergence and responsibility for the choices we make about our future. We have inherited extraordinary capabilities from millions of years of evolutionary experimentation, but we have also inherited the obligation to use those capabilities wisely. The story of early human evolution also provides crucial insights into the relationship between environmental change and evolutionary innovation. The climatic instability that characterized the Pliocene and Pleistocene periods created the selective pressures that drove the evolution of enhanced intelligence, technological sophistication, and social cooperation in our lineage. Without these environmental challenges, human ancestors might well have remained relatively simple apes, living stable lives in African forests. But environmental change remains a powerful force that can drive species to extinction, just as readily as it promotes evolutionary innovation. The same climatic fluctuations that spurred human brain evolution also eliminated countless other lineages that were unable to adapt quickly enough to changing conditions. The lesson for contemporary humans facing unprecedented rates of environmental change should be unmistakable. Our technological capabilities and social complexity do provide some protection against environmental disruption, allowing us to modify our surroundings and coordinate responses to challenges in ways that were unavailable to our ancestors. But these advantages don't make us immune to the fundamental forces that have shaped evolutionary history for billions of years. The pace of contemporary environmental change is occurring over decades rather than the millennia or millions of years that characterized past climatic shifts. While our technological abilities provide theoretical capabilities for responding to these challenges, our actual track record of coordinating effective responses to global environmental problems remains discouragingly limited. Understanding the experimental nature of evolution also provides important perspective on the future trajectory of our own species. Just as early human lineages diversified into multiple forms that explored different adaptive strategies, contemporary human populations may be beginning to diverge in response to different environmental and technological pressures. Advances in genetic engineering, artificial intelligence, space exploration, and other emerging technologies are creating new possibilities for human adaptation that were unimaginable even a few decades ago. Whether these developing capabilities will enhance human survival prospects or create new vulnerabilities remains an open question that will be answered by future events rather than current predictions. The history of evolution suggests that innovations which appear advantageous in the short term can become liabilities when conditions change unexpectedly. The massive brains that provided our ancestors with competitive advantages during the Pleistocene might prove to be metabolic burdens in a world facing different challenges. The technological systems that currently support human civilization could become points of failure if they prove unable to adapt to rapidly changing circumstances. The experimental nature of evolution means that there are no guarantees about future success, regardless of how well adapted any species appears to be at any given moment. The most we can do is try to maintain the adaptive flexibility that allowed our ancestors to survive previous environmental challenges, while remaining appropriately humble about our ability to predict or control the forces that will shape our future evolutionary trajectory. As paleontologists continue to uncover new fossils and develop more sophisticated analytical techniques, our understanding of early human evolution will undoubtedly continue to evolve. Each new discovery has the potential to overturn established theories and reveal previously unknown complexities in the story of how one particular lineage of African apes eventually gave rise to the remarkable diversity of human cultures and societies that characterize our contemporary world. The emerging picture suggests that human evolution was far more complex, experimental, and contingent than previous generations of scientists imagined. Rather than a simple progression from primitive to advanced forms, our evolutionary history resembles a vast network of interconnected experiments, most of which ended in extinction, while a fortunate few managed to survive long enough to contribute to the genetic and cultural heritage of modern humans. This perspective fundamentally transforms how we understand both our relationships with other species and our responsibilities for the future of life on Earth. We are not separate from or superior to the natural world, but rather integral participants in an ongoing evolutionary process that connects us to every other form of life through billions of years of shared history. The same creative forces that shaped our ancestors continue to operate today, generating new possibilities and eliminating old forms in an endless cycle of experimentation and selection. Understanding this connection should inspire both humility about our place in the larger web of life and determination to use our remarkable inherited capabilities responsibly for the benefit of future generations. We are the current inheritors of an extraordinary evolutionary legacy that spans millions of years and represents the survival of countless generations of ancestors who overcame impossible odds. We are also the first species in Earth's history to possess conscious awareness of the evolutionary process and the ability to influence its future direction through our choices and actions. The decisions we make today about technology, social organization, environmental stewardship, and our relationships with other species will determine not just our own future, but the future of the evolutionary experiment itself. The contingent nature of evolution means that outcomes are not predetermined, but rather emerge from the complex interactions between changing environments, available genetic variation, and the choices made by conscious agents like ourselves. This recognition brings with it both unprecedented opportunity and sobering responsibility. We have inherited capabilities that allow us to transcend many of the limitations that constrained our ancestors, but we have also inherited the obligation to exercise those capabilities with wisdom and foresight that takes into account the long-term consequences of our actions. The experimental nature of human evolution reminds us that our current success is neither permanent nor guaranteed. Like the robust Australopithecines and countless other extinct lineages, we could find ourselves poorly adapted to future environmental conditions that we cannot currently anticipate or control. The key to long-term survival may lie in maintaining the same adaptive flexibility that allowed our ancestors to navigate previous challenges, while avoiding the trap of over-specialization that doomed so many other promising lineages. As we stand at this unique moment in Earth's history, conscious inheritors of millions of years of evolutionary experimentation, we have the opportunity to write the next chapter in the ongoing story of life on our planet. Whether that chapter will be one of continued innovation and expansion, or of decline and extinction, will depend on the choices we make and the wisdom we bring to the unprecedented challenges and opportunities that lie ahead. The journey from one ape lineage to modern humanity has been marked by constant experimentation, frequent failure, and occasional breakthrough success. As we look toward an uncertain future, the lessons from our evolutionary past suggest that survival will require the same qualities that allowed our ancestors to thrive: adaptive flexibility, social cooperation, technological innovation, and above all, the humility to recognize that we are participants in a process much larger and more complex than any single species can fully comprehend or control. Control. The story of how our lineage survived when so many others perished becomes even more fascinating when we examine the specific environmental pressures that shaped the final stages of this evolutionary experiment. Around 300,000 years ago, Africa was once again experiencing dramatic climate shifts that would test the adaptive limits of every remaining human species. The continent was cycling through periods of extreme aridity, followed by sudden returns to wetter conditions. Lake levels fluctuated wildly, rivers changed course, and the boundaries between forests and grasslands shifted constantly across the landscape. For most species, these rapid environmental changes represented existential threats that pushed survival capabilities beyond their breaking points. But for one particular lineage, these challenges became opportunities. The ancestors of modern humans had developed something unprecedented in the primate world: the ability to consciously modify their behavior and technology in response to changing conditions faster than genetic adaptation could occur. This wasn't just behavioral flexibility. This was cultural evolution operating at speeds that biological evolution simply couldn't match. Archaeological sites from this period reveal technological innovations appearing and spreading across vast geographic areas within just a few thousand years. New types of stone tools designed for specific environmental challenges would emerge in one region and then appear at sites hundreds of kilometers away within relatively short time periods. This rapid cultural transmission suggests that early human groups had developed communication and social learning systems that were qualitatively different from anything seen in earlier species. The cognitive demands of managing these accelerated cultural changes created new selective pressures that drove the final phases of human brain evolution. The human brain reached essentially modern proportions during this period, but more importantly, it underwent internal reorganization that enhanced abilities for abstract thinking, symbolic representation, and complex social coordination. Evidence for these cognitive advances appears in multiple forms throughout the archaeological record. The first clear examples of symbolic behavior, including the use of ochre pigments and deliberate burial practices, date to this period. These behaviors suggest that early humans had developed the capacity for abstract thought and symbolic representation that would become such defining characteristics of our species. The development of symbolic thinking had cascading effects throughout human society and technology. The ability to represent abstract concepts through symbols allowed early humans to preserve and transmit information in ways that transcended the limitations of individual memory and direct observation. Knowledge about distant resources, seasonal patterns, and technological innovations could be encoded in symbolic systems and shared across groups and generations with unprecedented accuracy. This symbolic revolution also transformed social organization in fundamental ways. Early human groups could now coordinate activities based on shared conceptual frameworks rather than just immediate environmental stimuli. They could plan complex operations that extended across large geographic areas and long time periods. They could maintain social relationships with distant groups through symbolic exchanges that reinforced alliances and mutual obligations. The archaeological evidence for these enhanced social capabilities comes from multiple sources. Stone tool raw materials from this period show that some implements were manufactured from rocks that originated hundreds of kilometers from where they were eventually discarded. This indicates either long-distance travel by individual groups or participation in exchange networks that connected distant populations through chains of reciprocal relationships. The standardization of tool technologies across enormous geographic areas provides additional evidence for enhanced communication and social learning systems. Manufacturing techniques that required years to master were being transmitted between groups with sufficient precision to maintain consistent standards across distances that would have taken months to traverse on foot. Perhaps most remarkably, some archaeological sites from this period show evidence for specialized craft production that went beyond simple utilitarian needs. Carefully shaped stone tools that required enormous investments of time and skill to create, but showed little evidence of practical use, suggest that early humans were beginning to create objects for their symbolic, rather than purely functional value. This emergence of symbolic material culture represents a fundamental transition in human evolution. For the first time in the history of life on Earth, a species was creating objects whose primary function was to convey abstract information rather than to accomplish immediate practical tasks. These symbolic objects served as external storage devices for cultural information that could persist across generations and maintain social connections across vast distances. The development of symbolic behavior also had profound implications for human-environmental relationships. Early humans could now conceptualize and plan modifications to their surroundings that extended far beyond the immediate needs of survival. They could envision alternative environmental conditions and work systematically to create them through coordinated group activities. Evidence for systematic landscape modification appears throughout Africa during this period. Archaeological sites show that early human groups were using controlled burning to manage vegetation patterns across large areas. They were constructing water control features that enhanced the productivity of seasonal wetlands. They were selectively harvesting plant and animal resources in ways that promoted the abundance of preferred species. These environmental management practices represented a qualitative shift in the relationship between humans and their ecosystems. Rather than simply adapting to existing environmental conditions, early humans were beginning to actively shape those conditions to better suit their needs and preferences. This capacity for conscious environmental modification would become one of the most distinctive characteristics of our species. But environmental manipulation came with new responsibilities and challenges that early human groups had to learn to navigate. Poorly planned modifications could have unintended consequences that reduced rather than enhanced local resource availability. Overexploitation of particular species or habitats could lead to ecological degradation that undermined long-term survival prospects. The archaeological record suggests that early human groups gradually developed sophisticated understanding of ecological relationships and sustainable resource management practices. Sites from this period show evidence for rotation systems that allowed overused areas to recover while groups exploited alternative locations. They show seasonal scheduling of harvesting activities that maximized yields while maintaining breeding populations of important species. This ecological knowledge was encoded in the same symbolic systems that preserved technological and social information. Environmental management practices became part of the cultural heritage that was transmitted from one generation to the next through oral traditions, ritual practices, and symbolic representations. Groups that developed effective environmental management systems gained significant advantages over those that relied solely on short-term exploitation strategies. The integration of symbolic thinking, enhanced social coordination, and systematic environmental management created positive feedback loops that accelerated the pace of human cultural evolution. Groups that could effectively combine these capabilities were able to support larger populations, exploit more diverse environments, and maintain more complex social networks than their competitors. This competitive advantage became particularly important as human populations began expanding into environments that were increasingly distant from their ancestral African homelands. By 200,000 years ago, early modern humans were beginning to establish themselves in regions of Africa that had previously been uninhabitable for human populations. They were moving into desert margins, high-altitude environments, and coastal regions that required specialized technologies and knowledge systems for successful occupation. The archaeological evidence from these marginal environments shows remarkable technological creativity and adaptive flexibility. Early human groups developed specialized hunting techniques for desert-adapted animals, water procurement methods for arid environments, and food processing technologies that allowed them to exploit previously unusable plant resources. They created new types of shelters and clothing that provided protection from extreme temperatures and environmental conditions. Perhaps most importantly, they developed transportation technologies that allowed them to maintain connections with distant groups despite the challenging environmental conditions that separated different regions. The first clear evidence for systematic use of watercraft appears during this period, allowing early humans to cross rivers, lakes, and eventually marine barriers that had previously limited their geographic expansion. The mastery of water transportation represented another revolutionary breakthrough that opened up entirely new possibilities for human expansion and cultural exchange. Groups could now reach islands and coastal regions that had been isolated for millions of years. They could maintain contact across water barriers that had previously divided populations into separate evolutionary lineages. The cognitive and social demands of developing and operating watercraft created additional selective pressures for enhanced cooperation and planning abilities. Building boats required coordinated group efforts that extended over weeks or months. Operating them safely required detailed knowledge of weather patterns, water conditions, and navigation techniques that could only be acquired through extensive experience and cultural transmission. The archaeological evidence for early water transportation comes from multiple sources. Sites on islands that could only be reached by water contain human artifacts and fossils dating to this period. Coastal sites show evidence for systematic exploitation of marine resources that would have required watercraft to access efficiently. Stone tool raw materials from island sources appear at mainland sites, indicating regular transport across significant water barriers. The development of water transportation capabilities also had profound implications for human population genetics and cultural evolution. Watercraft allowed small groups to establish themselves in previously uninhabited territories, creating founder populations that could evolve independently while maintaining occasional contact with their source populations through continued navigation. This process of expansion and isolation, followed by renewed contact, created complex patterns of genetic and cultural exchange that characterized human evolution throughout this period. Island populations would develop distinctive local adaptations and cultural innovations during periods of isolation, then share those innovations with mainland populations when contact was re-established. The archaeological record shows that this process of expansion, innovation, and cultural exchange was occurring simultaneously across multiple regions of Africa and beyond. Different human populations were experimenting with different solutions to similar environmental challenges, creating a vast network of interconnected but semi-independent evolutionary experiments. Some of these experiments focused on developing enhanced hunting technologies that allowed more efficient exploitation of animal resources. Others specialized in plant processing techniques that could extract nutrients from previously unusable botanical materials. Still others concentrated on developing social and symbolic systems that could coordinate larger and more complex group activities. The diversity of these cultural experiments is reflected in the remarkable variety of archaeological assemblages from this period. Different regions show distinctive tool technologies, artistic traditions, and settlement patterns that reflect local environmental conditions and cultural preferences. Yet underlying this diversity are common themes of enhanced symbolic thinking, systematic environmental management, and increasingly sophisticated social coordination. The global pattern that emerges from this archaeological evidence is one of accelerating cultural evolution, driven by enhanced cognitive capabilities and social learning systems. Human populations were not just adapting to their environments, they were actively transforming those environments while simultaneously developing new technologies and social systems that increased their adaptive capabilities. This positive feedback loop between environmental modification, technological innovation, and social complexity created conditions that favored continued expansion into new and more challenging environments. Human groups that had mastered the techniques for surviving in marginal African environments were well positioned to adapt to the even more challenging conditions they would encounter as they began expanding into Eurasia and beyond. The transition from African to global human populations represents one of the most remarkable adaptive radiations in the history of life on Earth. Within just a few tens of thousands of years, human groups had established themselves across virtually every terrestrial environment on the planet, from tropical forests to Arctic tundra, from mountain peaks to desert valleys. This unprecedented geographic expansion was made possible by the same combination of symbolic thinking, social cooperation, and technological innovation that had allowed early humans to survive the environmental challenges of late Pleistocene Africa. But successful adaptation to global environments required scaling up these capabilities to handle challenges that were orders of magnitude more complex than anything human ancestors had previously encountered. The archaeological evidence from early sites outside Africa shows that human groups were continuously innovating in response to new environmental conditions. They developed specialized clothing and shelter technologies for cold climates. They created new hunting techniques for Arctic animals. They devised food storage and preservation methods that allowed survival through long winters when fresh resources were unavailable. Perhaps most remarkably, they developed transportation technologies that allowed them to cross the most formidable geographic barriers on Earth. The first human populations to reach Australia had to cross at least 90 kilometers of open ocean, requiring watercraft and navigation skills that approach the capabilities of much later maritime societies. The first Americans had to traverse the harsh environments of Beringia and then navigate through ice-free corridors or coastal routes to reach temperate regions further south. These achievements required not just individual courage and skill, but coordinated group efforts that could sustain complex operations across extended periods. The social and cognitive demands of organizing and executing such ambitious expansions created additional selective pressures that continued to drive human cultural evolution, even after our species had achieved essentially modern anatomical form. The result was the emergence of human societies with unprecedented capabilities for environmental manipulation, technological innovation, and social coordination. By 50,000 years ago, human groups were creating cave paintings that demonstrated sophisticated symbolic thinking and artistic abilities. They were manufacturing complex composite tools that required advanced planning and technical skills. They were establishing trade networks that connected populations across thousands of kilometers. These cultural achievements represented qualitative advances that went far beyond anything seen in earlier human species. The cognitive and social capabilities that made them possible had been building gradually over millions of years of human evolution. But they reached a critical threshold during this period that allowed explosive expansion of human cultural complexity. The archaeological record from this time shows evidence for the first complex ritual practices, the first sophisticated artistic traditions, the first systematic astronomical observations, and the first elaborate burial practices that suggest developed concepts of death and afterlife. These cultural innovations demonstrate that human consciousness had achieved levels of abstract thinking and symbolic representation that were qualitatively different from anything seen in earlier species. But perhaps the most significant achievement of this period was the development of cultural transmission systems that could preserve and accumulate knowledge across generations with unprecedented fidelity. Human groups were no longer limited by the cognitive capacities of individual members or the direct experiences of single generations. They could build upon the innovations and discoveries of their predecessors in ways that allowed continuous cultural advancement. This capacity for cumulative cultural evolution represented a fundamental transition in the history of life on Earth. For the first time, a biological species had developed the ability to evolve culturally at rates that far exceeded the pace of genetic change. Human populations could adapt to new environmental challenges within a few generations, rather than the thousands or millions of years required for biological adaptation. The implications of this transition extended far beyond human survival and expansion. The development of cumulative cultural evolution created the foundation for all subsequent human achievements, from the agricultural revolution to the industrial revolution to the information revolution that characterizes our contemporary world. But the same capabilities that allowed humans to transcend many natural limitations also created new vulnerabilities and challenges that our species is still learning to navigate. The power to consciously modify environments came with the responsibility to understand the long-term consequences of those modifications. The ability to accumulate knowledge across generations created obligations to use that knowledge wisely for the benefit of future generations. The archaeological record of this crucial period in human evolution provides both inspiration and warning for contemporary human societies. It demonstrates the remarkable creative potential that emerges when symbolic thinking, social cooperation, and technological innovation are effectively combined. But it also reveals the fragility of even the most successful adaptations when environmental conditions change beyond their adaptive limits. Understanding this history helps us appreciate both the extraordinary journey that led to our current capabilities and the ongoing responsibility we bear as conscious participants in the evolutionary process. We are the inheritors of millions of years of evolutionary experimentation, but we are also the first species with the power to influence the future direction of evolution itself. The choices we make today about technology, social organization, environmental stewardship, and our relationships with other species will determine not just our own future, but the future of the evolutionary experiment that gave rise to consciousness itself. The story of how one ape lineage became human reminds us that evolution is not a destination, but a journey, and we are still traveling. As we continue to uncover new evidence about our evolutionary past and develop new technologies that expand our capabilities, we face the same fundamental challenge that confronted our ancestors: how to use our remarkable inherited abilities wisely in an uncertain and rapidly changing world. The experimental nature of evolution means that success is never guaranteed, but the history of our lineage suggests that adaptive flexibility, social cooperation, and conscious innovation provide the best foundation for navigating whatever challenges lie ahead. The journey from one ape lineage to modern humanity has been marked by constant experimentation, frequent extinction, and occasional breakthrough success. As we look toward an uncertain future filled with both unprecedented opportunities and existential challenges, the lessons from our evolutionary past suggest that survival will require the same qualities that allowed our ancestors to thrive through millions of years of environmental upheaval and biological competition. We must maintain the adaptive flexibility that allowed early human populations to survive rapid environmental changes. We must preserve the capacity for social cooperation that enabled our ancestors to coordinate complex group activities and share crucial knowledge across generations. We must continue the tradition of technological innovation that has been the hallmark of human evolution since our earliest ancestors first began shaping stone tools. Most importantly, we must remember that we are not separate from or superior to the natural world that gave rise to us. We are participants in an ongoing evolutionary process that connects us to every other form of life through billions of years of shared history. The same creative forces that shaped our ancestors continue to operate today, and our choices will determine how that ancient story continues to unfold. The remarkable journey from one ape lineage to modern humanity reminds us that consciousness itself is an ongoing experiment whose outcome remains to be determined. We have inherited extraordinary capabilities from millions of years of evolutionary innovation, but we have also inherited the obligation to use those capabilities with wisdom, humility, and respect for the complex web of relationships that sustains all life on our planet. In understanding how we became human, we also come to understand what it means to be human, to be conscious participants in an evolutionary process that is far larger and more complex than any single species, yet which depends upon the choices we make as individuals and societies. The story of our origins is not just about the past. It is about our responsibility to shape a future worthy of the remarkable journey that brought us into existence. The weight of this realization becomes even more profound when we consider that the story we've been following isn't just ancient history. It's happening right now, in real time, as you listen to these words. The evolutionary forces that shaped our ancestors haven't stopped working. They're still operating, still experimenting, still testing new combinations of genes and behaviors and technologies to see what survives and what doesn't. Modern human populations are continuing to evolve, both biologically and culturally, in response to the rapidly changing environments we've created for ourselves. Some groups have developed genetic adaptations to high-altitude living within just a few thousand years. Others have evolved lactose tolerance or resistance to certain diseases based on their ancestral diets and disease exposures. These changes are happening faster than traditional evolutionary timescales would suggest, driven by the intense selective pressures of agricultural societies, urban environments, and global trade networks. But the most dramatic evolution happening today isn't biological at all. It's cultural. The same capacity for cumulative knowledge transmission that allowed our ancestors to develop complex technologies and social systems has now reached speeds that would have been incomprehensible to earlier generations. Information that once took decades to spread across continents now travels around the world in milliseconds. Innovations that once required generations to refine and implement can now be developed, tested, and deployed within single lifetimes. This acceleration of cultural evolution is creating new challenges that our species has never faced before. The environmental modifications that took our ancestors thousands of years to implement are now happening within decades. The social coordination that once involved small groups of related individuals now requires cooperation among billions of strangers. The technological innovations that once enhanced human capabilities in straightforward ways are now creating complex systems that sometimes seem to operate beyond human understanding or control. The archaeological evidence from recent millennia shows that human societies have repeatedly faced similar transitions between different scales of organization and complexity. The development of agriculture around 10,000 years ago required fundamental changes in social structure, environmental relationships, and technological capabilities that took centuries to fully implement. The emergence of complex civilizations involved additional transitions that challenged existing adaptive strategies and required new forms of cooperation and knowledge management. Each of these cultural transitions involved periods of experimentation, conflict, and reorganization as human societies learn to navigate new challenges and opportunities. Some groups successfully adapted to changing conditions and thrived in new environments. Others failed to make necessary adjustments and disappeared from the historical record. The same experimental process that characterized biological evolution continued to operate at cultural levels, but at dramatically accelerated timescales. The contemporary transition we're experiencing may represent the most significant challenge human societies have ever faced. The pace of technological and environmental change is now occurring faster than traditional cultural adaptation mechanisms can handle. The geographic scale of coordination required for addressing global challenges exceeds the capacities of existing social institutions. The complexity of modern technological systems is approaching levels that may be fundamentally incompatible with human cognitive limitations. Yet the same evolutionary history that brought us to this point also provides reasons for cautious optimism. Human lineages have successfully navigated environmental transitions before, often emerging with enhanced capabilities that opened up entirely new possibilities for survival and expansion. The cognitive and social adaptations that allowed our ancestors to survive previous challenges remain available to us today, even if they need to be applied in new ways and at unprecedented scales. The key insights from human evolutionary history remain relevant for contemporary challenges. Adaptive flexibility continues to be more valuable than narrow specialization when facing uncertain environmental conditions. Social cooperation remains essential for coordinating complex activities that exceed individual capabilities. Technological innovation provides tools for addressing challenges that would be insurmountable through biological adaptation alone. Cultural transmission allows beneficial innovations to spread rapidly through populations without waiting for genetic changes. But applying these evolutionary lessons to contemporary challenges requires understanding both their potential and their limitations. The same cognitive biases that helped our ancestors survive in small-scale environments can become liabilities when applied to global-scale problems. The social instincts that promoted cooperation within family groups can create conflict between larger populations. The technological capabilities that enhanced human survival can also create new vulnerabilities and unintended consequences. Recent research in evolutionary psychology and behavioral economics is beginning to reveal how our inherited cognitive and social tendencies influence modern decision-making processes. Understanding these evolutionary legacies can help us design social institutions and decision-making procedures that work with, rather than against, our evolved psychology. It can also help us recognize when our intuitive responses to contemporary challenges may be based on outdated assumptions about environmental conditions and social relationships. The fossil record reminds us that evolutionary success is never permanent and always depends on continued adaptation to changing circumstances. The robust Australopithecines were extraordinarily successful for over 1 million years before environmental changes made their specialized adaptations into evolutionary liabilities. Even our own species faced near-extinction events during the Pleistocene that reduced global human populations to just a few thousand individuals. These historical bottlenecks demonstrate both the fragility of even successful species and the remarkable resilience that can emerge from small surviving populations. The genetic evidence suggests that all contemporary human populations descended from groups that survived these prehistoric crises through some combination of technological innovation, social cooperation, and simple good fortune. We are the descendants of survivors, but survival required both adaptive capabilities and favorable circumstances that weren't entirely under their control. The environmental challenges facing contemporary human societies share some characteristics with the climatic fluctuations that shaped human evolution during the Pleistocene. Both involve rapid changes in environmental conditions that exceed the adaptive capacities of existing systems. Both require coordinated responses that go beyond individual or small group capabilities. Both present opportunities for innovation alongside risks of catastrophic failure. But contemporary environmental changes also differ from past challenges in crucial ways. The current rate of change is unprecedented in human evolutionary history, occurring over decades rather than millennia. The global scale of coordination required exceeds anything our ancestors ever attempted. The technological complexity of modern systems creates new vulnerabilities that didn't exist in simpler societies. The sheer size of human populations means that failure could have consequences far beyond anything experienced by earlier generations. Understanding these differences is crucial for developing effective responses to contemporary challenges. Strategies that worked for small populations facing local environmental changes may not scale up to global populations dealing with planetary-scale transformations. Technologies that enhanced survival capabilities in simpler environments may create new risks in complex, interconnected systems. Social institutions that promoted cooperation in traditional societies may be inadequate for coordinating activities among billions of strangers. Yet the fundamental principles underlying evolutionary success remain relevant even at these unprecedented scales. Species that maintain multiple adaptive options tend to survive environmental transitions better than those that become overly specialized. Populations that can share information effectively and coordinate responses to challenges have advantages over those that rely solely on individual capabilities. Groups that can innovate rapidly in response to changing conditions are more likely to thrive than those that remain locked into traditional approaches. The challenge for contemporary human societies is learning to apply these evolutionary principles at scales and speeds that our ancestors never encountered. This requires developing new forms of social organization that can coordinate global-scale activities while maintaining the flexibility and innovation capacity that have characterized human evolution from its earliest stages. It requires creating technological systems that enhance rather than replace human capabilities for adaptive decision-making. It requires building cultural institutions that can preserve and transmit crucial knowledge while remaining open to new information and changing circumstances. The archaeological evidence suggests that successful cultural transitions typically involve periods of experimentation during which different groups try alternative approaches to new challenges. Some of these experiments succeed and spread to other populations. Others fail and are abandoned. The overall process resembles biological evolution in its reliance on variation, selection, and inheritance, but operates much faster and can incorporate conscious planning and intentional design. Contemporary human societies are currently engaged in exactly this kind of cultural experimentation. Different countries and regions are trying alternative approaches to energy systems, economic organization, environmental management, and social coordination. Some of these experiments will prove successful and influence global patterns of development. Others will encounter problems and be modified or abandoned. The outcome will depend on both the intrinsic merits of different approaches and the environmental and social conditions under which they're implemented. The evolutionary perspective suggests that this experimental process is both necessary and unavoidable. No single approach to contemporary challenges is likely to work under all circumstances or for all populations. Success will probably require a portfolio of different strategies that can be applied flexibly depending on local conditions and changing circumstances. This diversity of approaches provides insurance against system-wide failures while creating opportunities for continued innovation and adaptation. But maintaining this experimental approach requires resisting the temptation to lock in particular solutions before their long-term consequences are fully understood. The history of human evolution is filled with examples of seemingly successful adaptations that became evolutionary dead ends when environmental conditions changed. The robust Australopithecines were extraordinarily well adapted to their immediate environments, but their specialization prevented them from adapting to new challenges. Similar risks exist for contemporary societies that become overly committed to particular technological or social systems. The key is maintaining what evolutionary biologists call evolvability, the capacity to continue adapting in response to changing circumstances. This requires preserving diversity in approaches to key challenges, maintaining redundancy in critical systems, and avoiding premature optimization around particular solutions. It also requires developing learning systems that can quickly identify and respond to emerging problems before they become catastrophic. Recent advances in complex systems science are providing new tools for understanding and managing these evolutionary processes at large scales. Network theory helps us understand how information and innovation spread through populations. Resilience science provides frameworks for building systems that can maintain essential functions despite major disruptions. Adaptive management approaches offer strategies for learning and adjusting policies in response to new information and changing conditions. These scientific advances are complementing traditional sources of wisdom about evolutionary processes. Indigenous societies around the world have developed sophisticated understanding of ecological relationships and sustainable resource management practices through thousands of years of cultural evolution. These traditional knowledge systems often incorporate principles of adaptive management, diversity maintenance, and long-term thinking that are directly relevant to contemporary challenges. The integration of scientific knowledge with traditional wisdom may provide the best foundation for navigating current transitions successfully. Modern science excels at understanding complex systems and predicting short-term consequences of interventions. Traditional knowledge systems excel at maintaining sustainable relationships with environments over very long time periods. Combining these complementary strengths could create approaches to contemporary challenges that are both scientifically informed and evolutionarily tested. But successful integration requires overcoming significant barriers to communication and cooperation between different knowledge traditions. Scientific and traditional approaches often use different vocabularies, operate at different temporal and spatial scales, and embody different assumptions about human-environment relationships. Building bridges between these approaches requires patience, humility, and genuine respect for different ways of understanding complex problems. The urgency of contemporary challenges makes this integration work particularly important. We don't have the luxury of waiting for gradual cultural evolution to produce optimal solutions to global-scale problems. We need to accelerate learning processes while avoiding the premature lock-in that has trapped previous societies in evolutionary dead ends. This requires unprecedented levels of cooperation between different groups and knowledge traditions. The fossil record reminds us that evolutionary transitions are rarely smooth or predictable. They typically involve periods of instability during which existing systems break down before new ones become fully established. Some lineages that seem well positioned to survive these transitions end up going extinct, while others that appear marginal manage to find new niches and thrive. The outcomes often depend on factors that are difficult to predict in advance. This uncertainty doesn't mean that conscious effort and planning are irrelevant to evolutionary outcomes. The archaeological evidence shows that human societies have repeatedly influenced their own evolutionary trajectories through technological innovations, social institutions, and environmental modifications. The capacity for conscious adaptation has been one of the key advantages that allowed human lineages to survive and thrive, despite environmental challenges that eliminated many other species. But conscious adaptation works best when it's informed by understanding of evolutionary processes and realistic assessment of both opportunities and constraints. This requires abandoning simple narratives about progress and technological solutions in favor of more nuanced understanding of complex systems and evolutionary dynamics. It requires accepting uncertainty while taking action based on the best available information. It requires maintaining hope while preparing for multiple possible futures. The story of human evolution provides both inspiration and sobering perspective for this challenge. Our lineage has successfully navigated environmental transitions that eliminated countless other species, demonstrating remarkable resilience and adaptive capacity. But our success was never guaranteed and often depended on factors beyond conscious control. Many other human lineages, with sophisticated technologies and complex societies, ultimately went extinct when they encountered challenges they couldn't overcome. The difference between survival and extinction often came down to maintaining the adaptive flexibility that allowed rapid response to changing circumstances. The lineages that survived were those that kept multiple options open, maintained diversity in approaches to survival challenges, and preserved the capacity for continued innovation when existing strategies proved inadequate. These same principles remain relevant for contemporary human societies facing their own unprecedented challenges. As we stand at this unique moment in Earth's history, inheritors of millions of years of evolutionary experimentation, we have both extraordinary opportunities and unprecedented responsibilities. We possess technological capabilities that would have seemed magical to our ancestors, but we also face challenges that exceed anything previous human societies ever encountered. The decisions we make over the next few decades will determine not just our own future, but the future of the evolutionary process that gave rise to consciousness itself. The journey from one ape lineage to modern humanity has been marked by constant experimentation, frequent failure, and occasional breakthrough success. The same experimental process continues today, but now we are conscious participants who can influence its direction through our choices and actions. The outcome is not predetermined, but will emerge from the complex interactions between our inherited capabilities, the environmental challenges we face, and the wisdom we bring to navigating an uncertain future. The weight of understanding our evolutionary journey becomes even more profound when we realize that the story we've been following represents just one thread in what was actually an intricate tapestry of experimentation. The fossil sites scattered across Africa tell us that between 2 and 3 million years ago, our continent had become a living laboratory where multiple human lineages were simultaneously testing different approaches to survival. Picture Eastern Africa during this period as a vast testing ground where nature was running parallel experiments in consciousness. Some lineages were developing increasingly sophisticated tool technologies while maintaining relatively modest brain sizes. Others were investing enormous metabolic resources in brain expansion while keeping their toolkits simple. Still others were specializing in processing specific types of foods that required powerful jaw muscles and enlarged grinding teeth. The remarkable thing about this period is that none of these approaches was obviously superior to the others. Each represented a viable strategy for survival in the challenging environments of Pliocene Africa. The robust Australopithecines, with their massive chewing apparatus, were extraordinarily successful for over 1 million years. The tool-using early Homo species were establishing themselves across diverse habitats. Various other lineages were finding their own niches in the complex mosaic of forests, woodlands, and emerging grasslands. So here we are, the unlikely survivors of an extraordinary evolutionary lottery that played out over millions of years across the changing landscapes of Africa, from Toumai's puzzling skull in the deserts of Chad to Ardi's remarkable blend of arboreal and bipedal adaptations, from the robust Australopithecines with their nutcracker jaws to the big-brained early members of genus Homo. We've witnessed nature's grand experiment in what it means to be human. The story we followed tonight isn't just about bones and stones scattered across ancient dig sites. It's about the profound recognition that our existence hangs on an impossibly thin thread of circumstance, adaptation, and sheer evolutionary luck. We are not the inevitable outcome of progress marching steadily forward. We are the temporary winners in a chaotic experiment where dozens of other lineages, each remarkable in their own way, tested different solutions to the challenge of survival, and ultimately came up short. Understanding this humbling truth should fundamentally change how we see ourselves and our place in the natural world. We carry within our DNA and our behavior the legacy of millions of years of experimentation. But we also bear the responsibility that comes with being the first species capable of consciously influencing the direction of evolution itself. The same forces that shaped our ancestors continue to operate today, but now our choices determine which experiments survive and which disappear forever. As you go about your life, remember that you are walking upright because countless generations of ancestors maintained the adaptive flexibility that allowed them to navigate environmental upheavals that would have crushed more specialized lineages. You possess consciousness because your lineage invested in the costly but ultimately transformative expansion of brain size. You can create tools, share knowledge, and coordinate with strangers across the globe because your ancestors developed the capacity for cumulative cultural evolution that allowed innovations to build upon each other across generations. The experimental nature of evolution means that our current success is neither permanent nor guaranteed. But it also means that the future remains unwritten, shaped by the same principles of variation, selection, and inheritance that brought us this far. Whether humanity continues to thrive or joins the countless extinct lineages in the fossil record will depend on our ability to maintain the adaptive flexibility, social cooperation, and innovative spirit that allowed one particular ape lineage to become human. The journey continues, and we are all participants in the next chapter of this remarkable evolutionary story.